Hi everybody. So I decided to record this online lecture in place of class today so that nobody had to venture out in the snow that we had this morning, though it looks like it's clearing up now. So our next topic is factoring polynomials. So it's something that you probably learned some skills in high school algebra, factoring, especially quadratic polynomials. And so we are going to tackle this problem a little bit more generally and a little bit more abstractly. So just to, get us started, there's a couple of things we have to define precisely when we're talking about factoring so we know what we're talking about. So first, for example, the type of stuff you learn to factor in high school are things like x squared minus 1. And you learn that that's equal to x plus 1 times x minus 1. So that can be factored. So this is an example of what we would call a reducible polynomial because we can factor it into two smaller polynomials. Now, it depends, though, what coefficient ring we're talking about. Because if we take something like x squared plus 1, well, we can't factor that over the real numbers, or the integers, or the rational numbers, but we can factor it over the complex numbers, right? So that's equal to x plus I times x minus I. So this is what we call a reducible polynomial over C, while it's irreducible over, say, the real numbers. So the field or ring of coefficients that we're talking about makes a difference in determining how or if we can factor polynomials. We also want to rule out kind of trivial factorization, so like we don't want to say, well, this is negative 1 times negative x squared minus 1. We don't want to really count that as a factorization. So let's define some terms so that we are precise about what we mean about factoring. So let's start with an integral domain. Apologies for the loud noises with this pencil on the iPad. And let's have a polynomial whose coefficients come from that integral domain. And let's say it's not the zero polynomial, and it's not a unit either. So a unit, again, depends on the integral domain. So for example, if we were working over Q, we wouldn't want any constant polynomial because that would, over the rational numbers, constants are units because, f of x equals 2 has an inverse f of x equals 1/2. So we're ruling out anything that's a unit, which, if we're working over a field, is any constant polynomial. So we say that f is irreducible over d if there's no way to factor it into two non-units. So if you can write f as, say, g times h, where g and h are also defined over d, if the only way you can factor f is if one of those factors is a unit, so like, for example, that would be like up here, the only way we could factor x squared plus 1 over the integers is, well, negative 1 times negative x squared minus 1, but negative 1 is a unit. So if that's the only way you can factor unit times something, then we say our polynomial is irreducible over d. Otherwise, if we can factor it into two non-units, then we call f reducible. Over d. Alright, so our big overarching goal is to develop some techniques and some strategies given a polynomial to determine whether it's reducible or irreducible. And this is a hard problem. There isn't any really magical theorem or technique to handle every situation. It's really just some techniques that work sometimes in some cases, and a lot of times it's really hard. In fact, in my own research right now, I am working with certain polynomials, and I would love to know if they're irreducible, because if they are, there's all these theorems I can use, and I'll have the results that I want, but I don't actually know if the polynomials that I'm working with are irreducible, and it's something that's been, giving me a hard time for a few weeks now. So this can be a really hard problem, is the point, and our goal is just to develop some techniques to be able to answer this question sometimes. So let's look at some basic examples. So let's start with something like 3x squared plus 6. Now, this is irreducible over, say, the rational numbers, but it's actually considered reducible over the integers, because we can write it as 3 times x squared plus 2. Now, this doesn't really count as a proper factorization over Q, because in Q, 3 is a unit. But in Z, 3 is not a unit, so this counts as a reduction. Again, the ring that you're working over, you really need to specify, because that does make a difference in deciding whether your polynomial is reducible or irreducible. So another instance where the ring or field you're working with matters is something like x squared minus 3. So that is irreducible over Q. You can't factor it with coefficients as rational numbers, but you can factor it over R, because we can write it as x plus square root of 3, x minus square root of 3. So those coefficients are no longer rational numbers, but they are real. We can also think about reducible versus irreducible over finite fields. So let's think about x squared plus 2. This is irreducible over z5, and but it's reducible over z3. Now, over z3, one thing that you can notice is that if you plug in 1 into the function, you get 1 plus 2, you get 3, which is 0, right? So since 1 is a root, is a 0 of this function, we should be able to factor out an x minus 1. Now, what does the other factor look like then? Let's see, x minus 2 probably will do the job. That certainly gets your x squared, it gets your 2, and then, if you expanded this fully, you'd get x squared minus 3x plus 2, which of course, if we're working in Z3, that's the same as x squared plus 2. So over Z3, we can factor it, and we were able to factor it because we noticed that we had a 0, right? When we plug in 1, we get out 0, so x minus 1 is a factor. So to check that it's irreducible over Z5, one way to do it is to check that it doesn't have any roots. So over Z5, f of 0 is 2, f of 1 is 3, f of 2 is 4 plus 2, which mod 5 is 1, f of 3 is 9 plus 2, which mod 5 is also 1, and f of 4 is 16 plus 2, reduce that mod 5, and you get 3. So there's nothing you can plug in Z5 that gives you 0, so that means there's no linear factors. And if we start with a degree 2 polynomial and we factor it, it would have to factor into 2 linear factors. Either that, it would be a unit times a quadratic factor, which doesn't count. So because there's no root, there's no 0, there's no linear factor, and so there's no factorization. So that's how we can show it's irreducible over Z5, but reducible over Z3. Now, if you're curious about the case that's been plaguing me in my own research, well, here's one of the examples. There's a bunch, but say you have the polynomial 1 minus 2x plus 3x squared minus 4x cubed, and you can continue this as long as you want. Let's stop there. I would love to be able to show that polynomials of this form, continuing on making it whatever degree you want, are always irreducible over q, over the rational numbers, but I don't actually know. So if you want to play around with that example, and if you can make any headway on it, I would be very interested in knowing. So if you're looking for a challenge, try those polynomials. See if you can show those are irreducible. Now, in order to show something is irreducible, we need some tools. So let's develop some techniques. So the first is one we kind of talked about on the last slide. We showed that a polynomial was irreducible over z5 just by checking that it didn't have any roots, right? So it didn't have any linear factors. Now that will work if you're working over a field and if your polynomial has degree 2 or 3. So let's say we have a field and a polynomial defined over that field, and the degree is either 2 or 3. Then we know f is reducible over f if and only if f has a 0 or a root in f. Now that's just because if we're working over a field and we have a degree 2 polynomial, the only way to reduce it is to turn it into a product of 2 degree 1 polynomials. And every degree 1 polynomial corresponds to a root. And similarly, if we had a degree 3 polynomial, if we were to factor it, it would factor into a degree 2 and a degree 1. And so that degree 1 polynomial would give us a root. Now, this only works for degree 2 or degree 3. So for example, this theorem doesn't help us at all with a degree 4 polynomial, because there's always the possibility that it doesn't have any zeros, doesn't have any linear factors, but maybe it has 2 quadratic factors. So this doesn't really help us determine reducibility for higher degree polynomials, but for degree 2 or 3, this does the job. So oftentimes, lots of the theorems that we have about factoring and reducibility are applied to when f is a field, rather than just any general integral domain. Now, oftentimes we'll be working with polynomials with integer coefficients, but we'll want to determine if it's irreducible over q, over the rational numbers, not over the integers. So that means we want to check, does it have any factors where the coefficients maybe aren't just integers, but could be rational numbers as well. That maybe seems like a harder problem because there's more possibilities for factoring when you're dealing with rational numbers than if you're just dealing with integers. But it turns out it doesn't make the problem any harder, thanks to Gauss. So I have a definition and then a lemma and a theorem for you. So first, I want to tell you what I mean when I say the content of a polynomial. So if you have a polynomial defined over the integers, say, the content of f is just the greatest common divisor of all of the coefficients. And if the content is 1, so if there isn't a common factor to all of your coefficients, then f is called a primitive polynomial. That means there's no constant that you can factor out. All right, so just as an example, if we take a function 12x cubed plus 6x squared minus 14x plus 8, the content of f here would be 2. because we can factor out a 2 from every coefficient, and that's the greatest factor that we have. So that's content. Now we have a very important lemma from Gauss, which I will talk about on the next slide. So Gauss's lemma, one of Gauss's many results, is that if you have two primitive polynomials and you multiply them together, the result is still primitive. So this isn't obvious at first glance. Maybe f and g, there isn't any constant you can factor out. But when you multiply them, multiplying two polynomials, there's all these cross terms. It's kind of complicated in what the new polynomial looks like. Maybe it works out that, everything in that product polynomial, all the coefficients are suddenly multiples of 2 or something. So this lemma says that doesn't happen. And so let's sketch out a proof here. So let's set up a contradiction. Let's suppose that f and g are both primitive, but their product is not. So suppose f and g are primitive, but fg isn't. So that means there's, say, a prime number p such that P is a divisor of all of the coefficients of fg. So let's think about reducing these polynomials mod p. So let's say maybe f bar is f with all the coefficients reduced mod p, g bar is g with all the coefficients reduced mod p, and fg bar is when you take the product and reduce all the coefficients mod p. Now this last one is 0 by our assumption, because if p is a divisor of all the coefficients, then when you reduce mod p, you just get 0 for every single term. Alright, so that means, f bar times g bar equals 0, working over zp. But zp is a field, and so we know that the polynomial ring is an integral domain. So we have no 0 divisors, so this means that either f reduces to the 0 polynomial or g reduces to the 0 polynomial. So that's just because we have no 0 divisors here. Alright, well, if f of x or g of x reduce to the 0 polynomial, that means all of their coefficients are multiples of p. So that implies that these are not primitive. So f or g is not primitive, and that's our contradiction. And that completes our proof. So the product of two primitive polynomials is a primitive polynomial. Now, why do we care about this? It's useful for the theorem I'm going to show you on the next page, which tells us how to relate irreducibility over z to irreducibility over q. So here's our theorem. So let's say we have a polynomial with integer coefficients. If f is reducible over q, then it's reducible over z. So what does this mean? It means, if we're asking ourselves, can we factor this polynomial with integer coefficients, we don't have to worry about trying to factor it, into factors with rational numbers, and maybe that's possible when factoring it with integer coefficients is not. This says that that never happens. If you can factor it over the rational numbers, then you can always find a factorization that works over the integers. Let me just show you an example of what I mean by this. So say we have a function 10x squared minus 7x plus 1. And let's say I'm factoring it over the rational numbers. One way to factor it is 5x minus 5 halves times 2x minus 2/5. All right, but let's say I don't want to factor it over the rational numbers. I want to factor it over the integers. This theorem tells us I should be able to do that. If I can factor it over the rationals, I should be able to find a factorization that works over the integers. So the way to do that is, let's just kind of multiply both sides by 10 to get rid of the denominators. So I'm going to multiply the first factor by 2 and the second factor by 5. Alright, so all I did there is multiply both sides by 10 to get rid of the denominators on the right-hand side. Alright, so now what I'm going to do on the right-hand side is factor out the common factors I see in each piece. So we have 5 times 2x minus 1 times 2 times 5x minus 1. And then this 10 cancels with the 5 and the 2. And so the polynomial that we started with has an integer factorization, 2x minus 1, 5x minus 1. So this theorem essentially says you can always do this. If you can find a factorization over the rational numbers, then you can always find a factorization over the integers, essentially by following this exact process. And the key piece to showing that this process always works is actually Gauss's lemma. So now that we've seen an example, let's work on proving the theorem. All right, so let's suppose we have a factorization, f is reducible over q. All right, and we may assume that f is primitive. Because if it were not primitive, we could just factor that common factor out of f and then also factor it out of g and then just cancel it out. Since g and h are defined over a field, you can factor any number out even if it's not there. It will just, potentially produce some denominators. So we can assume f is primitive, otherwise just factor out and cancel from both sides that common factor. So we're going to kind of mimic what we did in the example. So g and h, the coefficients are rational numbers, so they might have denominators. So first thing you want to do is rewrite g and h so that all your coefficients have a common denominator. So say a is that denominator for the coefficients of g, and let's say b is the denominator for the coefficients of h. Then, what we did in the example at this point, we multiplied by those denominators. So that's what we're going to do here. But I'm going to write it on the next slide since we are running out of room. All right, so we have f is g times h. And I'm going to multiply by a and multiply by b. And now, if we take g of x and multiply by a, and we take h of x and multiply by b, that essentially clears out all of the denominators. So now we are working with polynomials with integer coefficients. All right, so each of these now is defined over the integers. All right. So let's give names to the content of each one. So let's say C1 is the content of AG, and let's say C2 is the content of BH. All right, so what we saw last time in the example, we had a common factor in G and a common factor in H that we took out, and it exactly canceled with the AB that we had on the left. We had a 10 on the left, and we had a 2 and a 5 on the right. And it turns out that will always happen. So this means we can write A times G as C1 times some primitive thing that I'll call G1. And this means when we look at BH, we can factor out a C2, and then what's left is primitive. So we have AB times F is equal to C1 G1 times C2 G2. Where on this side, since F is primitive, when we multiply by AB, that becomes our content. And here, since G1 and G2 are primitive, the content is C1, C2. But since they're equal, AB must equal C1, C2, and so we can cancel those out, and we get f of x equals G1x, G2x. Now, two important things that I kind of glossed over here is that G1 and H1 are now defined over the integers. So what we have here is a factorization over Z, whereas before G and H were only defined over the rational numbers. So we've shown that if we have a rational factorization, then we have an integer factorization. Another piece that I glossed over is at this step right here, when we argued that the content was C1, C2, we argued that because G1, G2 is primitive. Now, I'm saying G2 when it should be H1. Sorry about that. Let's fix that. All right, so we know G1 is primitive and we know H1 is primitive because we factored out the content. Gauss's lemma tells us that G1 times H1 is still primitive. And so the content of this whole big product is just C1 times C2. So this step is where we used Gauss's lemma. All right, so this says if we can factor it over the rationals, then we can always factor it over the integers, using the strategy outlined in this proof that we used in the last example. So that means we don't have to worry when we're trying to factor over Q about all the possible fractions we could use as coefficients. We just have to check to see if we can factor it over the integers. Oftentimes, what's useful here is the contrapositive of this statement. So the contrapositive of this statement says if f is irreducible over z, then it's irreducible over q. All right, so if you can't factor it with integer coefficients, then you won't be able to factor it with rational coefficients, even though it seems like there will be more options and that maybe you can. So this is good news. This means when we have a polynomial with integer coefficients and we want to know if we can factor it over q, we only need to check if we can factor it over z, over the integers. We don't have to worry about fractions in our coefficients. All right, so let's use this new knowledge to develop some tests to check to see if a polynomial is irreducible. So there's two tests I want to show you today that are quite useful. One is called the mod p irreducibility test. It basically says, so if you have a polynomial defined over the integers, And p is a prime number that you've chosen very wisely. And f is not constant, so let's say the degree is at least 1. And you look at the reduction mod p. So this is, again, the polynomial where you just take every coefficient and reduce it mod p. Now, if the degree doesn't change when you reduce it, so it's potentially possible, if your leading coefficient is a multiple of p, that when you look at f bar, the degree goes down. But if that doesn't happen, and if f bar is irreducible over zp, then f is irreducible over q. All right, so this is a good test because checking that something's irreducible over a finite field is usually easier than checking that a polynomial is irreducible over, the rational numbers, or as we know now, over the integers. Just because over a finite field, you usually only have like a finite number of possible factors to check. But this can still be kind of hard to use. Now, I don't want to prove this formally, but just to kind of see why this is true, it's basically true because of the contrapositive. So if you could factor it over q, right? So if you had a factorization over q, then we know we have a factorization over z. So let's say this is a factorization over z. Then you could just reduce everything mod p, and you'd have right here a factorization mod p. So this says if you can't factor it mod p, then you can't factor it over q. The reason why that's true is because if you can factor it over q, you can just reduce each factor, and then you get a factorization over p. You got to be a little bit careful. That's why we need this degree statement. But that's essentially the crux of why this is true. So let's look at an example to see how we can use this. All right, so let's look at 5x cubed plus 3x plus 1. All right, so this is degree 3. So if it factors, it would factor into a degree 2 and a degree 1. Now, that means we just need to check that, it doesn't have any roots. So what we're going to do is we're going to reduce mod 2. So if we reduce mod 2, all odd numbers just reduce to 1. So this is x cubed plus x plus 1. And now we just have to check that this does not have any roots in z2. So if we plug in 0, we get out 1. If we plug in 1, we get 1 plus 1 plus 1, which mod 2 is equal to 1. So there's no zeros. And since this is degree 3, that means this is irreducible over z2. And our mod p test says that means that this is irreducible over q. All right. So using the mod p irreducibility test involves choosing a prime, reducing modulo that prime, showing your polynomial is irreducible over zp, and then you can conclude that it's irreducible over q. Now, you have to be careful. Your choice of p really makes a difference. Sometimes you'll choose a p and you'll find that your polynomial is reducible over zp. That doesn't mean it's reducible over q. This is not an if and only if statement. So this only works for irreducibility. You cannot use it to conclude that any polynomial is reducible over q. Only works for irreducibility. And the prime that you choose, you really have to be careful and choose wisely, because some of them will work, some of them will do the job for you. So 2 worked here, but some of them won't. For example, if we tried to reduce mod 3, the same example, we would get 2x cubed plus 1. Now here, x equals 1 is a 0, right? If we plug in 1, we get 0. So this means x minus 1 is a factor. So that means we can factor this somehow. Let's see, we would need a 2x squared, and then maybe plus 2x to cancel out that middle term. All right, that'll give us a minus 2x plus 2, something like that. So this is reducible over Z3. That tells us nothing about whether or not it's reducible over Q. So some primes just won't work for this test, but some will. So using this test involves some strategy, picking the right prime that will get you the result that you want. You can't always find one, but sometimes you can. Sometimes this works. So here's an example that's a little bit harder. Let's look at 3x to the 4th plus 7x cubed minus 11. So degree 4 is harder, right? Because it's not enough to show that it doesn't have any roots. You also have to show that you can't factor it into two quadratic factors. So let's look mod 2 and see what we get. So we get x to the 4th plus x cubed plus 1. Right, and we'll check to see that it doesn't have any roots. So 0 and 1 both give you 1. So this means there's no degree 1 factors, no linear factors. So if it factors, if it's reducible, then it would have to look like a quadratic times a quadratic. So x squared, potentially plus x, maybe not, plus 1, times x squared plus maybe something plus 1. Where a and b, remember, either have to be 0 or 1. We're in Z2. So if we can factor it, it would have to factor like this. So let's just show that that doesn't work out. So if we expand this, we get x to the 4th plus a plus b x cubed plus, let's see, 2 plus ab times x squared plus a plus b x plus 1. So just equating our coefficients, looking at our x cubed coefficient, we see a plus b has to be congruent to 1. But looking at our x coefficient, our linear coefficient, it's also a plus b, but there is no x on the left-hand side. So this says a plus b has to be 0. So this is impossible. These can't both be true. And so there is no such factorization. So we ruled out the only possibilities. There's no linear factors, there's no quadratic factors. And so that means our reduced polynomial is irreducible over Z2, and our mod P test says therefore f is irreducible over Q. All right, so that one was harder. There was more work to do. It wasn't enough just to plug in numbers and show that it doesn't have any roots. We also had to rule out another option. And maybe you can see that when you move to even higher degrees, there's even more possibilities to rule out. So this problem is very hard when you're working with polynomials of degree 4 or higher. All right, I have one more useful test for you, and it's for polynomials of a particular type. So if you have a polynomial with integer coefficients, an xn plus blah, 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 plus a constant term, if there exists a prime p such that p is not a divisor of an, but p does divide all the other coefficients, and p squared does not divide a 0, then f is irreducible over Q. So if your coefficients have this property for some prime, then we can argue that f is irreducible. So I'll explain why in just a bit, but first we'll do an example. So if you have a polynomial like x to the 7th plus 21x to the 6th minus 3x to the 4th plus 12x squared minus 9x plus 15, this is what we call an Eisenstein polynomial. And we usually say it's Eisenstein at 3, meaning it has this property for p equals 3. Right? So by that we mean this coefficient is not a multiple of 3, but the rest of them are. And this one is not a multiple of 3 squared. Right? So it meets all the criteria. And so Eisenstein's criterion says this is irreducible. All right, so this works just for a very special and particular type of polynomial. Now, why is it true is the question. Just to give you a flavor rather than a formal proof. Well, let's suppose it were reducible. And let's say g of x is equal to b r x to the r, just to give names to the coefficients. And let's say the coefficients of h are c's. And let's suppose that f is as written up here, and it meets all these criteria. So then an is brcs, and a0 is b0, c0. Right, so let's first look at this one. So we know p is a divisor of a0, but p squared is not. So that means p is a divisor of b0 or c0, but not both. Right, so let's say p divides b0, but not c0. All right. So we know here p doesn't divide an, so that means p doesn't divide br, and p doesn't divide cs. All right, so I'm running out of room. I'm going to continue the argument on the next slide. All right, so we know that p divides b0, p does not divide br. So let's let t be sort of the smallest number such that p does not divide bt. So look at b0, then b1, then b2, then b3. Find the first one that is not a multiple of p, and we'll call that bt. And then let's look at the corresponding coefficient in f, at. Well, if you kind of FOIL out the product of g and h, this is bt times c0 plus bt minus 1 times c1 plus everything up to b0 times ct. All right, so all of these, by definition, are multiples of p, right? Because we're assuming that p divides b0, b1, b2, up to bt minus 1. You know, t is the first one it does not divide. But here, this thing here is not a multiple of p. So that means AT is not a multiple of p, because if you take a multiple of p plus something that's not a multiple of p, the result is not a multiple of p. But remember, we're assuming that this is an Eisenstein polynomial, so all of the a's except for the first one are multiples of p. So this is a contradiction. Which means that we can't factor our polynomial. It is truly irreducible. So that's why Eisenstein's criterion works. As a corollary, this will probably be the last thing I talk about today. I know this is starting to run a little bit long before giving you some examples. As a corollary, if you look at what we call a cyclotomic polynomial, so that's usually a capital phi sub p, and it's what you get when you take x to the p minus 1 and divide it by x minus 1. And you just get x to the p minus 1 plus x to the p minus 2 plus blah, 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 plus x plus 1. You know, a polynomial where the coefficient of everything is 1. We can show that this is irreducible. over q for any prime p. And the trick is a useful one for proving irreducibility. So what we're going to actually show is that phi of x plus 1 is irreducible. And then argue that if phi of x plus 1 is irreducible, then phi of x must be irreducible. So let's do that over on the next slide. So let's let f be phi of x plus 1. All right, so that is, x plus 1 to the p minus 1 divided by x plus 1 minus 1. So that's, let's see, the denominator there is just x, so let's leave that out for now. And then the top thing, if you use the binomial theorem to expand that, that's x to the p plus p choose 1 times x to the p minus 1 plus p choose 2 times x to the p minus 2. And the last thing will be plus 1 minus 1, so the constant term cancels out. So p choose p minus 1x, I guess will be the last term. And then if we divide through everything by x, we get x to the p minus 1 plus p times x to the p minus 2 plus whatever p choose 2 is times x to the p minus 3. And our last term is p, once we factor out and divide by that x. So this is an Eisenstein polynomial. All of these coefficients are multiples of p. This is not a multiple of p squared, and our leading term is not a multiple of p. So this is Eisenstein at p, so it's irreducible. So what we showed is that phi of x plus 1 is irreducible. But that means phi must be irreducible. And why is that? Well, let's just think sort of contrapositive. If phi were reducible, then phi of x would be, g times h. But then phi of x plus 1 would just be g of x plus 1 times h of x plus 1. Right, so if it were reducible, then phi of x plus 1 would also be reducible. So the fact that this is irreducible means this is irreducible. So that's kind of one trick sometimes for showing that a polynomial is irreducible. If you can't show that f of x is irreducible, well, show that f of x plus 1 is irreducible, or f of x plus 5, or f of x plus any constant. Changing your input by just adding or subtracting a constant isn't going to change the ability to factor that polynomial, right? It'll just change what the factors are. So that's one trick you can have up your sleeve. If you're trying to do like an Eisenstein argument or a mod p irreducibility argument and it's just not working out, you can't find the right prime to use, sometimes using this idea of just kind of shifting things, replacing x with x plus a constant, gives you a new polynomial that might be easier to show as irreducible. All right, so here are 3 polynomials. They are all irreducible over the rational numbers, and I want you to explain why for each one. So take a moment, pause the video, and try to use the irreducibility tests that we've talked about today. So the mod p irreducibility test or the Eisenstein's criterion to show that each of these polynomials is irreducible. So pause the video, try it on your own, and then I'll be back in just a second to explain the solutions. All right, have you done it? If you didn't pause, please pause now. Last chance, I'm going to start explaining the answers. All right, let's go. So, for the first one, this is an Eisenstein polynomial. If we choose 2. If you look at our coefficients, the first coefficient, the leading coefficient, is not a multiple of 2. All subsequent coefficients are multiples of 2. And the last one is not a multiple of 4. that meets all of the criterion, and so we can say that it's irreducible. For the second one, this is not an Eisenstein polynomial because the only thing that could work is 2, but our last coefficient is a multiple of 4. So we can't use Eisenstein's criterion. So let's try to use the mod P irreducibility test. Now, I usually try mod 2 first, and that doesn't work in this case because you just get x cubed, which is reducible, x times x times x. So let's try mod 3. So if we reduce mod 3, we get x cubed minus x plus 1. All right, so since this is cubic, degree 3, if it did factor, it would have to have a degree 1 factor. So it would have to have a root. So we can just check by plugging in 0, 1, and 2, and checking that this doesn't have any zeros. And that's enough to argue that this is irreducible over Z3. So if we plug in 0, we get 1. If we plug in 1, we get 1. If we plug in 2, 8 minus 2 plus 1 is 7, which is 1. So we get 1 no matter what we plug in. We never get 0. So this is irreducible over Z3, which means by the mod P irreducibility test, it's irreducible over Q, over the rational numbers. All right, now the third one I think is the hardest. There's no Eisenstein criterion, right, because these coefficients don't have anything in common. So that's not going to work. So we can try some mod P irreducibility tests. You'll find that mod 2 doesn't work. Mod 2, you get 0 as a root. Mod 3 won't work either. If you reduce mod 3, I think 1 works out as a root. So I went to mod 5. And when I reduce mod 5, I get x to the 4th plus 3x squared plus x plus 3. All right, so to check that this is irreducible, because it's a degree 4 polynomial, it's not enough to check that it doesn't have any roots, but that's a good first step. So we could plug in 0, 1, 2, 3, and 4, just to make sure it doesn't have any linear factors in Z5. So 0 gives you 3, 1 gives you 1 plus 3 plus 1 plus 3. That's 8, which is 3. If you plug in 2, let's see, you get 1 plus 2 plus 2 plus 3. I think that's 3. If you plug in 3, let's see, 3 to the 4th is 1. 3 times 3 times 3 is 2. 1 plus 2 plus 3 plus 3 is 9, which is 4. And if we plug in 4, which is also negative 1, we get 1 plus 3 minus 1 plus 3. We get 6, which is 1. So we don't have any roots. So that means if it factored, it would have to factor into 2 quadratic things. And we can assume the leading coefficient is 1, because if not, we can just sort of multiply by the inverse so that it is. We're working over a field, so every coefficient is a unit. So let's say it's x squared plus ax plus b times x squared plus cx plus d. Now we just need to rule this out by, playing some algebraic games here. So let's do that on the next slide because it's going to take some space. So we had x squared plus ax plus b times x squared plus cx plus d, and that was equal to x to the 4th plus 3x squared plus x plus 3 in Z5. All right, so expanding over here, we get x to the 4th plus a plus c x cubed plus, let's see, d plus ac plus b times x squared plus ad plus bc times x plus bd. All right, so that means a plus c has to be 3. AC plus D plus B has to be, I'm sorry, A plus C is 0. There is no cubic term. The quadratic term is 3. The linear coefficient is 1, and the constant coefficient is 3. All right, so we just need to check to see if this is possible. So, system of equations, let's do some algebra. So C is negative A. So let's start with that. And then down here, we can say D is 3 over B. Again, we're working over a field, so every element has a multiplicative inverse. That's not 0, so we don't have to worry too much about dividing by things here. And so that solves for D and C in terms of A and B. So let's rewrite these just in terms of A and B. So that'll be negative A squared plus 3 over B plus B equals 3. And AD, so that's 3A over B plus BC, so that's negative AB equals 1. So I'm going to multiply by B so we don't have denominators. All right, so here I can maybe solve for A. And then I can just maybe at this point try all my combinations for B and see if it works here. So, all right, let's start. So we know B times D equals 3, so we know B can't be 0. So there's 3 options, and let's just check if any of them work. I'm just going to do an exhaustive search here. So first, if B is 1, A is 1 over 3 minus 1, 1/2. Now the inverse of 2 in Z5 is 3. So now if B is 2, A is 2 over 3 minus 4, so that's negative 2, which is 3. If B is 3, then A is 3 over 3 minus 9. Negative 6 is the same as negative 1, so that's negative 3, which is 2. And if B is 4, A is 4 over 3 minus 16. So that's 4 over negative 13, which is the same as negative 3. Let's see. The inverse, negative 3 is 2. And 4 divided by 2 is 2. So we have 4 combinations to check here. B is 1 and A is 3. B and 2 is A is 3. B is 3 and A is 2. B is 4 and A is 2. And just check to see if any of them satisfy this. So the first case, I'm going to write them up here in this blue box because I'm running out of space on this slide. So if B is 1 and A is 3, this equation tells us negative 9 plus 3 plus 1 equals 3. Now that is not true, because this is 0. That failed. So let's try B is 2 and A is 3. Then we get negative A squared B. So we're plugging into this and checking to see if it works. So that's negative 9 times 2. So that's negative 18 plus 3 plus 4 equals 6. So that is negative 11 equals 6. Negative 1 equals 1 mod 5. That is not true. And you can similarly check the other cases when B is 3 and A is 2, and when B is 4 and A is 2, and see that this is never satisfied. So there is simply no way to write this polynomial as a product of 2 degree 2 polynomials. And since that was the only possibility left, we can then conclude that this is irreducible over z5, and therefore the original polynomial that we started with must be irreducible over the rational numbers. So as you can see, showing that a polynomial is irreducible can be a lot of work, and it can be a very difficult problem. In general, it's a hard thing to solve, to decide whether a polynomial is reducible or irreducible, but we'll see later that irreducible polynomials are so essential to constructing certain types of fields and to lots of things in algebra, and there are lots of theorems that apply only to irreducible polynomials. So when you can decide, when you can show that a polynomial is irreducible, you usually have a lot more powerful tools at your disposal. So it's important, and it's a nice thing to be able to do when we can, though it's an awfully hard problem, and I think mathematicians are actively looking for more and better and newer irreducibility tests. So these are just a couple of tests. There are many more out there that are more complicated, but in general, this is a hard problem that we as mathematicians don't always know how to solve. So next time we'll talk about, why do we care about whether a polynomial is irreducible or not? What can we do with that information? And what can we prove and what can we construct? And so we'll do all of that together on Tuesday. If you have any questions about this, I'm going to put a survey up, the usual homework question survey, and you can put your questions on that survey, or we can talk when we see each other on Tuesday. So have a great weekend, and I will see you next week.